that those are equivalent, which means that if I look at the means between those two populations, the mean value, which I said has some problems with tails, outliers and whatever, but the mean value, if the two samples are taken from the same population, then they should have fairly similar means. And this is literally where we get to invoke the central limit theorem, because the central limit theorem is about differences between values and their means. So you can actually end up using that to talk about how likely is it that I would get these two different mean values from two different random samples. Okay? And if they are, then I can look at that. So the formula for the T statistic is the mean of the first population minus the mean of the second population divided by the standard deviation of those two populations. Okay? And a word of caution, standard deviations come in two forms. The sample standard deviation, which is really, the difference between them is, I'm going to take the sum of x minus x bar squared, and I can divide by 1 over n, or I can divide by 1 over n minus 1. Okay, those are the two different formulas. This is the sample standard deviation. This is the population standard deviation. And the default for different softwares are different. In R, this is what standard deviation means. In Excel, this is what standard deviation means. And in Python, in SciPy, that's what standard deviation means. So if you ever read something, you might find a slightly different number because they just are sloppy and say standard deviation, and they assume you can infer is it the sample or the population. But the real basic rule is if I have a bunch of data, I generally should be using the sample distribution because that's what I have. I have a sample. Okay. So if I look at this, and I'll come back to the reporting conventions in a second. Right, I have a bunch of samples. The vertical axis here is the sort of value of the samples. I take their mean, and I compute the standard deviation. I can compute the mean of this one and take the standard deviation. So when I say the standard deviation of x1 and x2, I'm going to take, actually no, I take it back the other way. I said this population standard deviation, not the sample. Maybe I got them backwards. I would have to check. But this, the denominator here is the square of the first standard deviation divided by n plus the square. It's the harmonic mean of the two standard deviations. Okay? So that formula goes into what this T statistic is. And what it's really saying is, in terms of what you might think of as error bars, if this mean, if this is the probability of the mean being someplace else, is this mean likely to have the same value as that, to just randomly occur? And if you look at sort of this probability, if this is really the probability of this occurring, that's pretty unlikely in these two samples. So for those two pieces of data, the statistic would actually be rejecting the hypothesis that these two distributions are the same. If I hadn't shown you all the statistics, I just showed you the dots on the left and the dots on the right, you'd likely say, yeah, those are two different performances, right? This set of dots is different from that set of dots. And they are. So visually, this is sort of confirming what you would have seen from the statistics. So when we talk about data, so for this data, and I'm sorry I got these two slides sort of mixed up, the reporting convention would be the T statistic for this actual set of data, 11.9, degrees of freedom is 9, and then P is less than 0.0001. Okay? And it's 9 because there are 9 points here. The degrees of freedom are the number of samples that go into your calculation minus 1. So there should be 10 points there. Okay? And that gives us what we're going to do. Okay? So that was the basic t-test. It's actually really simple. If I have a bunch of data, I compute the data. Actually, let me go back to that, right? All I have to do is I compute the average over my experiment and the standard deviation over my experiment for algorithm 1, and the mean and the standard deviation for algorithm 2, and then I combine them and I get this t statistic. And then for however many samples I use, and this is where it becomes important to understand what's a sample. If I'm measuring runtime of my algorithm, then it's how many runs of my algorithm did I do with different inputs. Okay? If it's how many folds that I do in cross-validation for machine learning, then it's every fold that I would be looking at. Okay? And this is where, in a computer, it's pretty easy. If my statistics suggest but are not good enough because P is not large enough, right? The formula that lets me actually use the degrees of freedom, the higher the degrees of freedom, the more data I have, the more difficult it is for two means to be very different. So if I actually have a mean of 1.00001 and a mean, another sample of 1, are those two things statistically significantly different? Okay? And I'll go a little bit farther. The standard deviation is 1. So the standard deviation here is actually quite large. This is probably not. On the other hand, even with a standard deviation of 1 and that difference, if the sample population was 1 million, it probably is significant. Right? That's just from experience. I've known that to play with lots of numbers. So it's not just enough to look at the data and the standard deviation. You also have to look at the number of samples. But as a rule of thumb, coming back to just looking at papers, if I have the erasure, that would be good. I don't. If somebody has done a good job, and this is why error bars and plots are good, if I have two algorithms, my red and my green algorithm, and I draw them, and we sort of talked about this before, right? Is one of these better than the other? We don't really know. But if I draw a standard deviation right, over it, right, for where my samples are, then I might be able to say, in fact, if I've drawn one standard deviation, standard deviations, 3 standard deviations generally give you 99% confidence. Because a Gaussian, if I'm here 3 standard deviations away, this probability is 0.989 or something like that. 2 standard deviations is 0.85, 1 standard deviation is 0.65. Right? So just 1 standard deviation is often not enough to be statistically significant, but it sometimes is, because the answer of statistical significance depends on how many samples I ran. In fact, much smaller, even if the curves overlap in their error bars, the results might still be statistically significant if I ran them with enough data. So error bars are a rough thing. If the error bars, however, are huge, right? So if I got rid of the red and they look like this, right? And that's the standard deviations, then yeah, your statistics are going to be, as long as you ran 10, 20, those would be significantly different because there's so many standard deviations away. It doesn't take much with a small sample and large differences. Okay, so when we talk about the t-test, what I just showed you, when I go to apply the t-test, and actually I'm going to take a excursion and fire up Excel. No, it isn't. Maybe it's in my slides. Thought I had it in here, but I remembered I didn't save the last version. So in Excel, I have to. In Excel, I can actually equal plus t-test. Okay, I've just started a function that says t-test. Is that not readable? I have to make it somehow bigger. Come back over here. This is probably why I shouldn't have done that, but okay. I don't know if it's any more readable, because I think although my font is bigger, it doesn't show the help stuff in the bigger, does it? Anyhow, so there's something here. Actually, I'll do it this way. I'll go up here and I'll click on. No, I can't see. Where's the little help function? And I'll do it over here. So Excel has a built-in help function. Go over here. And so if I click on the formal builder, I do t-test. Then if I click down here, it will actually show me the help screen. And for some reason it's saying it's not available. Don't tell me it's not available. I know it's available. Does that say t-test?
Yes.
Okay, let's try that. Okay. Quit. Here. So it's taking its time trying to get me the help. Okay, so here's the help for the t-test. The t-test takes 3 arguments: an array for the first column of data, an array for the second column of data, sorry, four things. Then there is a number of tails, which I'll talk about in a second, but there's the last one. The number of tails is actually asking a question. So when I ask if these two are equal, right, which is the null hypothesis, that's called a two-sided test. I'm not saying which one is better than the other. It turns out the math of how to get there is a little bit weird, so I'm not going to go into the details of what that looks like. But if I want to answer this question, it's called a one-sided t-test. And it turns out the probabilities basically come from, am I looking, if here's one mean and here's another, right, I'm asking what's the likelihood of the area on one side or the other. Sorry, it's actually the difference between these. So there's some area of the curve. I can actually have it on both sides, which is why it's called two-sided. If I don't know if this one is supposed to be bigger or less, the second tail lives over here and there's more of it. The two-sided test is what I recommend in general you use to solve this problem. You make a second hypothesis. If they are unequal, I can look at one of the means and say, my mean is better than their mean. My mean is smaller, bigger, whatever is necessary, right? And then use the fact that they're not equal to say, well, then mine is better because my mean is lower. The difference between a one-sided and a two-sided t-test turns out to actually be, for almost any reasonable degree of freedom, double. So the two-sided test has the p-value will be double the p-value of a one-sided t-test. Okay, so you will find in places in papers where they play a game and they say, I'm going to use a one-sided t-test because it gives me a p of 0.04. But that means from a two-sided t-test, their p-value would have been 0.08. It might not have been significant. So anytime you see somebody using a one-sided t-test and it's really close to the boundary, then it's questionable whether or not things are very different from random. Okay? Because if the two-sided t-test is actually doing a more powerful thing. It's saying, is it likely that my value is less than another value? Okay? The real reason for doing a one-sided t-test isn't because I wanted to do less than or equal, but that's the way some people end up using it. The reason to do a one-sided t-test, the only statistically justified reason, is because I'm comparing it to a known value, to an absolute ground truth. Okay? So, for example, if I'm answering the question, is a coin biased or not, we know theoretically an unbiased coin has 0.5. So if I flip it 100 times and I get a mean of 0.499, now I can use a one-sided t-test to compare 0.499 and 0.5. Because 0.5 is not a measurement. 0.5 is an absolute number based on theory. That's the only time you use a one-sided t-test. You will find people using them incorrectly to try and solve this because they're saying, no, I only want one side. The second part, and that's really the difference between a two-sample and a one-sample. And in my view, a one-sample t-test is really the only time to use a one-sided t-test. I will also say I think I'm in the majority of what statisticians say. There are some that will say there are theoretically justifiable times to use a one-sided for other reasons. But my view is, if you're that close to deciding if it's significant or not, double your data, use the two-sided so there's no question whether or not you're playing games, right? Just get more data. In computer science, that's generally pretty easy. So the next problem I want to talk about is what's called a paired t-test. Doing things. How do I make that? Okay, yeah, actually, I will, that was actually probably good. I should not have gone on to, I'll do tails. No, I did tails, right? So now I'm going to do type. So let's talk about paired t-test and I'll bring that help back. So when I'm doing a bunch of measurements, and this is pretty common for computers, right? If I run two algorithms on exactly the same block of data, I have a bunch of data A, B, C, D, right? But I think of these as my test sets, and I run two algorithms, 1 and 2 on these, right? The results of these use exactly the same data, and the data is where the randomness lives. So we can call these paired tests because they used exactly the same data. On the other hand, if I bring in two human subjects and I use one human subject in algorithm A, another human subject in algorithm 2, they are not paired. They're not the same person. Okay? Now there is a way to do pair tests with humans. It's generally for before and after or pre-post tests, where I have the same person before and then the same person after. So if I do pre-algorithm post, I can compare these with a paired test. So those are the two most common reasons to have a paired test. Same person before and after, or two different things on exactly the same data that came from someplace else. And the reason paired tests are useful is if I look at the two populations. So if I look at this distribution and I try and answer the question, are these different? Actually, those distributions probably are different. But, so I probably should have drawn a more complicated one. If I actually have two distributions that look like this, right, it's hard to say if these distributions are different. They're very broad compared to the difference in their means. If, however, every time this number occurred, this number occurred, if all I really did was shift the curves, then in a paired test, every time this number shows up, this number shows up. And now if I gave you two algorithms and I said, algorithm A is always equal to 2 plus algorithm B in terms of accuracy. Is algorithm A better than algorithm B? Right? Algorithm A is always 2 points better than algorithm B on every sample you run. Doesn't matter what it is, right? It's 2% more accurate. Then algorithm A is probably more accurate than B. Now we can get to that statistically through this idea of a paired test. If every time I run these two, this gives me this first low value, next experiment gives me this middle value, right? They're all paired up. Then I can use what's called a paired t-test, which instead of looking at the population differences, looks at the population of the differences. It says, how likely is that population of differences to occur if they actually have the same distribution? Okay. And if one of these that quickly happens, and so if you remember I said there were these non-parametric versions, the match for these paired t-tests is the WILCOXON signed rank test. Okay? And the word sign there is actually important because if every one of these tests has the same direction, right, one algorithm is always better than another on every block of data, the sign test is going to end up saying that's significant because if these were two random variations, it was all noise, then sometimes algorithm A would be better, sometimes algorithm B would be better. And it's actually just looking at how often is that to occur randomly. So the sign pair test is much more powerful in detecting differences. So if I come back over now to the Excel help, in the Excel help, the third parameter has a value, which is the type. If it's equal to 1, it performs a paired t-test. If it's equal to 2, it performs a 2-sample equal variance test. And then if it's 3, it'll do a 2-sample unequal variance test, only a static version. So the difference between those, let me go back. So here, this test, where's my mouse? Oh, let's get rid of this guy. Oh, missed it. So this test is unequal variances, the homeostatic test, or heterostatic test, because each of these has different variances. The type 2 test in Excel assumes that these two are the same and only computes it once. Actually, it assumes they're the same and it computes it over the entire population. And the difference is, the bigger the amount of data I compute over, the better my estimate of the variance becomes, which then increases the power of the statistical test. So those type 1, 2, and 3 are actually most powerful, second most powerful, third most powerful. And then after that, you're going to go to the WILCOXON sign rank test, or the WILCOXON rank test or sign rank test, because those are the things that don't require assumptions. So those were all pretty straightforward. So to sort of summarize the t-test or t-like tests, if you have intervals that are measured and parametric, you can use the independent samples t-test, which is the first version where I might compare to an absolute value. So if I have a scale that I believe is meaningfully approximately linear, like agree, disagree, a Likert scale, slightly disagree, whatever. These are pretty common in stuff. And for lots of these, people believe that those are relatively linear. Then you can use an independent sample test, and answering the question, do people agree, is a comparison against an absolute of the middle, because that was I'm neutral. So if I test, are they equal to 3, I can say no, people aren't neutral. Then I can look at the value of the mean and say, is it a positive or negative intent? And if I have related samples, this thing I just talked about, it's the paired t-test. And I like to try and design my computer experiments to use paired t-tests, okay? Because it's very powerful. It'll show a difference when other things may or may not. And to do that, I have to assume that my runs are relatively independent. If I choose my data and I make independent blocks, then the dependence between these algorithms are not what matters. The independence is on the random data. So if I take my data and I break it up into pieces, okay, which is standard if I'm going to do something like cross-validation, then I will get things that I can run 2 different algorithms on. I get a t-test, and I can do a paired t-test to say, is algorithm 1 better than algorithm 2? Okay, and that's a powerful way of defining even small differences between algorithms become pretty sensitive when you're doing that. If, however, I don't have enough control over this data, then I might not be able to assume it's independent, and then I would be looking at either the Mann-Whitney U-test or, as I said, the WILCOXON rank test, WILCOXON rank test. There's a bunch of these. My recommendation for you is if you're in your computer science degree here and you're running into problems, come find somebody for help. Your advisor, or come find me sometime later. I can help people with basic statistics to get some of this done, right? I can answer which kind of test you should be using. I'm not going to do the statistics for you, but I can tell you what package to go use. That's as far as I will generally get. Okay. Oh, see, I did put it in. Couldn't see it when I was looking for it. So the Excel function takes these arguments, the array. So if you put all your stuff in an Excel spreadsheet, it takes 30 seconds to run a t-test. That's why it's like, why aren't people doing it? Well, if you didn't run enough experiments, it's a different problem. But once you run enough experiments, it's easy to do this. Okay. One thing to note about the Excel t-test, it doesn't actually give you the t-value. It gives you the likelihood of the t-value. That is, it gives you the p-value. Okay. And the reason it can do that is because it knows the degrees of freedom because it ran the size of the array. Okay. If somebody already computed it and you don't have all of the individual items, you can still do a t-test by hand, but you can't just use Excel to do it. You have to use a table or something else. So the value that comes out is literally p for your p-value for your test. As I mentioned, this WILCOXON sign rank test is the one to use when you have paired data, when the data is not normal. So even though I said if I break this up, I get the assumption of independence, I actually needed 2 things. I needed independence and ordinal continuous numeric data. If this is a bunch of survey data where the answers include 1, 2, 3, and 1 and 2 is not the same as 2 and 3, then really we should be using something like the WILCOXON sign rank test, and that's a time to go pulling it out. So the basic idea of this, I'm going to go through it very quickly. You basically exclude differences that are 0. You put the rest of them in ascending order. You ignore their signs. You basically just look at them and say, assign them ranks. Okay? And if their differences are equal, average the ranks. So, and I'll go through a numeric example in just a second. And then you're going to count up the ranks of how many were positives and how many were negatives. And if there's no difference between the treatment, your algorithm, between the positives and the negatives, then you would expect these would be similar, independent of the distribution. This is why it's more powerful. If there were a difference, one sum would be much larger than the expected, and the smaller the sum is denoted by t, and then we look at those two. And then there's a table of values which you look up. to decide what are the critical values or what are the statistics to decide what the number is. So the important part is to sort of walk through this, because although the real answer for this is if you want to do one of these tests, go call one from a library, right? Don't implement this yourself. Python, R, MATLAB, they all have a WILCOXON test built into them. But it's good to know a little about what's going on, because sometimes if you put one or two weird pieces of data in, you get some weird results. So it's good to have a feeling for what's going to go on. So if I look at the data, if I have the hours of sleep, Trey needs more. Treatment is 6, baseline is 5.2, the difference is 0.9. And you're going to see I'm going to rank that one as 3.5. 7.9 is minus 0.9. And that's because after I take this array, I'm going to have a bunch of numbers. I have 0.5, 0.6, 0.9, 0.9, which is really 3 and 4 in rank. So I just make them 3.5. So they're equivalent. And then all I really do is take the smaller value. In this case, I have 50.5 and 4.5. Right? So most of these you'll notice are positive signs. So after I find their ranks, it's going to say the average rank of the positives is 50.5, the average ranks of the negatives is 4.5, and if I go look that up in a WILCOXON some rank test, it'll tell me it's significant at about the 2% level. So P is around 0.02, right? So if the T value, or P value, P or T? T. Okay, T. If the T value is large, okay, so the T value, so when I go to look it up in the table, I have to tell it how many items are in the table. Okay, so if I have 100 items in the table, then T will always be larger than if I have 10 values in the table, because the ranks go from 1 to 10, and here they go from 1 to 100. So there will be, but on average, so if the numbers were equally randomly distributed, plus and minus, right? They'd actually, the rank will, if the hypothesis is not true, that is, if they're not very different, then it'll be around the middle of the list, of the length of the list, right? Because I'll have been adding 100 plus 1, right? That's 51, right? So the number will be, if I have 100 items, if the hypothesis is around true, then T will be around 500. Because it'll be 50 number, or maybe it's 250, right? Average of 50 of the value, 50 of those numbers go in. Right? So here, with 10 numbers, if all of them were positive, then the ranks would be 1 through 10, right? And that would be a sum of 55. Right? So if they're both near 25, then they're about the same. So when you say large depends on what it's expected based on the size of the table. However, if the T value is very small, given the size of the table, you're going to be very significant. But it's still good to go look up the P value because it depends on the size of the table. Okay, so far, we've been doing the most natural thing for some parts of computer science. We have compared two items, right? Algorithm 1 and algorithm 2. Okay, that's the easy stuff to do, and in my view, it's generally the best thing to do. So if you're going to do a comparison with the state of the art, you might actually have a plot with 10 algorithms in it. Okay, most of those algorithms are not that interesting. There's one out of that algorithm that was the previous state of the art. You included them all for completeness because number 3 might be the review of your paper, not number 1. You don't want to tick them off, and you want to show where they really. And often because the algorithms actually have behaviors where this is the performance of algorithm 1 and this is the performance of algorithm 2. There are places where algorithm 1 is better, there are places where algorithm 2 is better. You should know what those are. Now, but there are times when I really want to do a comparison of more than two groups, right? You know, what's the most heavy person in the family, right? Or, so, and this is where it becomes important, right? How do I want to do that? If I want to answer, you know, is the family all the same? Is a slightly different question than who's the heaviest person in the family, but we'll come back to that, right? So in all these, it's pretty easy. You can use a human look, but you did this in two different ways. One is I can do a pairwise comparison. I can ask, you know, Fred versus Wilma, Fred versus, I don't know the name of most of these people, whoever they are. I have no idea who any of these people are. So, but you know, to tell the difference between these groups, I could ask, are these groups the same? Are the individuals the same? There's a test called ANOVA, right? ANOVA stand, which we'll get into, right? But let me first explain the advantages and the disadvantages of what are called multiple paired comparisons. So the natural way, you now know how to compare 1 and 2. If I ask you to compare 1, 2, 3, 4, one way of doing it is I compare 1 and 2, I do 3 and 4, and I take the winner of each of those, right? And I compare the winner, right? Which is really maybe 1 versus 3. Bracket tests, right? This is the way we do lots of competitions. We do lots of pairwise computations. In fact, I could do 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, 3 versus 4, right? I can do all the pairwise comparisons. So the problem with that is the number of comparisons comes back to cause a problem in terms of the errors we have, right? Remember, the probability of an error in a single comparison, let's let that be error, the alpha error, the probability of incorrectly rejecting the null hypothesis, right? That was our type 1 error. That can happen. Well, if I can take 1 minus that number, I get the probability of making no error in a single comparison. Now, if I start making m comparisons, the probability of no errors in m comparisons, no type 1 errors in an m comparison, is 1 minus alpha to the power m. And 1 minus that number becomes the probability of an error in an experiment under the assumption that each of these is an independent comparison. It's actually, since I reuse 1, if I do 1 versus 2, 1 versus 3, not completely independent, so there's a few other things that go on. But the problem with that is if I started with an error of 0.5, right, or sorry, 0.05, right, 5%, okay, and I do 2 of these tests, right, so then what's my first one, my probability of making an error, of not making an error is 0.95, okay, but if I take 0.95 times 0.95, I don't know what that gives me, but it's like 0.9, 0.8 something, right? 0.8 something probably, right? So my error of a type 1, my probability of a type 1 error just went up significantly because I did 2 type 1 2 tests. If I do 4 or 5 of them, yeah, do 4 of them, so 0.95 to the 4th. I see a calculator out.
4814.
For 2 or for 4?
For 4.
For 4. So after 4 of these, right, it's 0.81 approximately, right? So now my probability of a type 1 error is 20%. Right? I started off with 5% error, but after I did a couple of them, my errors compound because every one of those interactions has a problem. So, in fact, at 4, you've already reached the limit, right? 2 or 3 of these might be okay. 2, maybe, but 3 or 4, you start running into problems. So the standard way we solve this is with a different type of test called ANOVA, which stands for analysis of variance, and we'll spend a little bit more time on this one. And the ANOVA test really comes in 2 forms. Actually, there's like 12, but 2 major forms. One-way ANOVA, which is similar to a t-test, except that it's only going to compare the means of 3 or more groups. T-tests only compare 2 groups. So if I got 3 or 4 groups, I do a one-way ANOVA. Okay, and then there's a two-way ANOVA, and it's useful when I have to compare variables that have 2 or more different independent variables. So in the t-test, the only thing I can vary is one thing. Right? I can't vary 2 dimensions. So here I broke up my data. If I actually wanted to have an experiment where I change size and weight at the same time, now t-tests can be applied along this dimension or along this dimension, but not both. Two-way ANOVA allows me to do something where I fill in all 4 of these and now ask how are my algorithms different. Okay. This slide is out of place, but I'll just do with it now. I talked about some other types, and I guess I put it here because of ANOVA's here, right? If I have continuous variables and categorical explanations, which is it's the same or it's same or different groups, then I would use ANOVA or possibly linear regression. If my groups are along a plot, I'm saying here's group 1, group 2, group 3, and I expect there to be a relationship between them, then I can do linear regression instead of ANOVA. The first things we had were continuous and dichotomous, meaning one or the other, di for two. If I have continuous variables and my output is a continuous variable, then I'm definitely doing some type of correlation, linear regression, nonlinear regression, because I have a continuous number in and a continuous number out. There are some other tests which I'm not going to have time to go into, but I do want to mention them because sometimes they're actually important for computer science. A dichotomous test, a choice of two variables, and I'm trying to decide which of two algorithms is better at choosing one of two variables, then I need to be doing something like logistic regression or a chi-square test, which is actually pretty common. Maybe I'll get that in next class. And then there's dichotomous and continuous, which is logistic regression, and time to event to a dichotomous, which is a logarithm. There's a bunch of other statistics. I'm not going to go through all of them, but I wanted to go through the ANOVA, which I might get through today, and I'll save anything else for next class. Okay, so I'm going to go through a sort of a long-winded explanation. This is based on stuff I borrowed from somebody else's slides, which should be in here, but it doesn't look like it is. So imagine that I'm looking at the intensity of gray matter for structures on MRI of normal and benign multiple sclerosis patients and a secondary progressive multiple sclerosis patients. I'm trying to decide, is increased hypointensity, brighter pixels, a marker of the disease? So I'm trying to decide across these three groups, normal people, early stage multiple sclerosis, and late stage multiple sclerosis, is there a difference? Okay. Now I'm going to say is there a difference in brightness of pixels, but you can imagine the same test could be applied if I'm saying, is an algorithm better at detecting something? Because it's really the same question. I just use brightness as the algorithm. It's the simplest algorithm you can get. Okay. So the null hypothesis is that on average, the output is the same, right? And this is a categorical predictor with a continuous outcome, which means we can use ANOVA. We can compare each of these groups by doing three pairwise tests. But if we do that, and I ask, so I will make this into real numbers here, what's the overall alpha level, the chance that I will reject something that I should not have? We just went through this math. So we did the alpha predicted, we compute 1 minus alpha. So if we did three pairwise tests at the 0.05 level, the chance that we fail to reject all three hypotheses is 0.85. Right? So now that doesn't mean that the failure to detect any of them is 0.05. It's the failure to detect all three simultaneously. Therefore, our probability of a type 1 error is 1 minus that is 0.14. Okay? That number is greater than 0.05, and this gets increased as things get worse. So if I'm trying to answer, are all these things the same, which is the null hypothesis, multiple t-tests aren't the best thing. Okay? So enter ANOVA, analysis of variance. And it's called that because it's really going to look at the null hypothesis that each of these have the same mean. So like we did before, we're going to have an assumption that they all have the same mean. Okay? And part of what it's going to look at is the variance. So the alternative hypothesis is that at least one of the means is different. But from ANOVA, and this is the most important part, which unfortunately Tree fell into this trap, is that you can't tell which. And I will show you how people sometimes play games with this in a little bit. Okay? The names tell us we're going to be using variance, but the goal is to actually use the variance to compare the mean. Okay? We're not actually comparing variances in the sense I'm saying whose variance is bigger. I'm saying, do the variances help me decide are the means different? And that's where it comes from. Okay. So basically, how does it work? As I said, we have a continuous outcome, but we're trying to decide a categorical variable. We have to consider the assumptions. Again, the underlying assumption, and this is stronger in ANOVA than it was in the t-test, is that the distribution of the populations are normal. For the t-test, I have to have the distribution of the difference between the means to be normal, right, which is a little bit weaker. Here, the variance of each group is equal. This is what we call the homeostatic test. In the type t-test, that was type 2. Okay? And so they're similar to a 2-sample t-test with equal variance in terms of some of their assumptions. And the basic idea is that if we all had the same mean, then the populations would look very much like the same graph. With some random variations, they tend to overlap similarly, but they have some variations. However, if the populations look very different, then we say there's a variation among the group. So what we're really looking for is there's a lot of overlapping groups, and then maybe one group that's not overlapping. And that's what ANOVA is looking for. But it's not actually saying it has to be one. It could be a continuous shift. It could be a whole bunch of these things going on. So when we take the samples from each group, there will be two sources of variability. The within group variability, the samples we get from the same group. So for your algorithm, that would be the variance I get for my algorithm on different sets of data. That's my within group variation. And the between group variability, the difference between algorithm 1 and 2 as I move across the data. Okay? And if all of this, and those are the two sources of variability. And so the question is, can we use these two types of variability to determine if the means are likely to do that? So if I think about the variations within the group, that's what my standard deviation measures. Within my group, I can look at my standard deviation. That's how much I randomly vary. Okay? The blue arrow, actually I guess it's the orange arrow, I don't know why it didn't show up in the color I wanted, is the within group, and the red arrow is the difference between the means. Okay? So in this drawing here, the within group is large, the between group is small. These are probably from the same distribution. But in this one, the within group is smaller than the between group. And these are probably from different distributions. And it goes through a much more complicated process than that, but that gives you an intuition of how it's doing it for all of the groups. It's looking at the difference between the variances within group and the variances between the groups to make this work. And given our time, I am going to skip over the derivation of this because it doesn't really matter that much. It's in the slides in case you want to see it. I guess I know how I did it. So in doing this, I want to explain some of the variables that show up so you can interpret your ANOVA data. So I guess I'll go through it very fast. So we start off with the variable. We talk about the mean of a group and the grand mean over all groups. Right? So I can talk about the mean over each group. So I have an x sub j bar, and then I have x double bar, which is the mean over all the groups, right? Which is actually the same as the mean of the means. It's, when you divide right, it gives you the right thing. Okay? So if I look at the sources of variability, there's really two differences. If I look at, try to compute variance, there's the difference between a variable and its mean, and the difference between the mean of that class and the grand mean. Those are the two different things that show up. So if I take this deviation and I start squaring it, because that's what I do when I do standard variance, if I look at the standard deviation of a variable from the grand mean, take its square, you can break that up into two parts. The difference between the variable and its mean squared plus the difference between the mean and the grand mean squared. We call the first of these the within group sum of squared means. The second is called the between group sum of squared means. And then the total is the total sum of squares. So depending on what software you use, they will actually report to you the within group sum of squared means and the between group sum of squared means. They will often have slightly different symbols, but SSB and SSW are common because that's within and between. Sometimes they'll just say SW, some will just say W, depending on what package you're looking at. And there's another variable we'll look at in just a second. So if we look at this, the result is that the within group mean squared error is the combined result of these two groups. And so many of them will not report, some will report the sum of square errors, others will report the mean square within group. Okay? And it doesn't really matter if it's the mean square or the sum of squares. There's obviously a scaling between them. But you should sort of understand that. So when you see them, you'll often see the mean square B and the mean square W, or again, sometimes they'll just say MB and MW for mean square. The drop, how many letters is going to show you. And that gives you an idea what's going to go on. So in doing the ANOVA, we then, after we've computed those numbers, you compute what's called the F statistic. And so in reading it, you'll see, well, we did ANOVA, here's our F. This is our F statistic, which is the mean squared of the between divided by the mean square of the within, which turns out to be the sum of the squares divided by the right scaling factors. Okay? The F statistic is then compared with an n minus k minus 1 and n minus k degrees of freedom to an appropriate table or appropriate local function. So that will give you something. So if I were to look at an ANOVA table from lots of forms, you'll basically see things where they're going to have sources of variation, and they'll have some labels like SDF, MSF, p-value, between, within, total. And then they'll fill in these numbers, and you can look at those. For example, if I did this with the Excel stat package or the SSPS, which is commonly used in social science, I'll show you some of the results. But let's go through a quick example. If here's our healthy, our summary statistics, healthy, these are the benign or the early stage MS, these are the late stage MS, right? Here's their means, here's their standard deviations, and here's their sample size. With that data, right, it gives you a general feel. Do you think there's a difference between healthy, benign, and late stage, right? Here's the differences in means, here's their standard deviation, here's the sample size. Are those different? Right? Now, imagine that this is actually not healthy, benign, whatever. This is algorithm 1, algorithm 2, algorithm 3. Right? Is algorithm 1 healthy? Is it different from the others? Is there a difference among these three algorithms, or are they all the same? It's really hard to tell looking at these numbers, right? But you'd see plenty of papers that would say, look, my mean is better than their means, I'm done. Okay? This is when you start running into problems. When you look at data, it's especially troubling when the sample sizes are different, because now it's really hard to draw any conclusions. You got to use the right tool. So if I were to look at the data, now when I looked at it this way, by the way, right, it was pretty hard to tell, is there a difference? Did any of you think there was or wasn't? Some of you already read the slides, so you know the answers. But now, if I show it to you visually, this is another way we do things in computer science. We sometimes mislead people by using good graphics. So now, if I were to show you this distribution, and I showed you the mean, I might say, look, HC is a better algorithm than BMS. Why? Well, see, the few points higher up, they seem to be overall better. The mean is a little bit better. Okay, but there's an awful lot of spread. So we do the real hypothesis test. Okay, we put them in, we get a continuous outcome predictor. You run through all this, the p-value turns out to be 0.0062. There is a difference between these data. And this is why statistics can actually be powerful and not powerful. Right? You look at this and it's hard for me to tell. I'm not sure. You run the statistics and it's like p is 0.006. That's significant. This is saying there's something different between these distributions. Okay, it doesn't, however, support that HC is better. It just says things are different. Okay. So here's the ANOVA table that comes out of it. The numbers for the between, within, degrees of freedom, the statistics, and then things come out and give you a value, simple value. Okay. Here's an even smaller value. Okay, so here I have three groups of performances: 5.3, 6, 6.7, 5.5, 6.2, whatever. Okay, are those the same or different? And again, the answer is you probably can't tell. Okay, now if I look at their means, okay, so the averages are 6, 5.9, 5, and 7.5, and then they have variances of 0.49, 0.17, 0.13. What do you think? Are they different now? Even with means and variances, still hard to tell, because this variance, so the value of 6, 0.49, 0.5, 7.5, these are probably different. The first two probably aren't, but the last one is probably different enough. Okay, so better or worse depends on if bigger or smaller is better. But, so to compute the ANOVA, you can sort of put together, look at the statistics, putting them together, and run this through. The degrees of freedom is one less than our number of groups. The number of individuals that were involved, so that's the total sum of the samples. Okay, and we have, a p-value of 0.008. So there is a difference. Okay, but you got to remember the assumption of normality, a couple of the other things. Now, if one of them wins, so if there's a difference, and you want to say your algorithm is better, you have a problem, because ANOVA doesn't answer is one better. It only answers which ones is there a difference. So if there is a difference, how do I decide? Well, I can go back to where I started, which has a danger. I can go back and I can do pairwise tests. Algorithm 1 versus 2, 1 versus 3, 1 versus 4. Okay. Now, the thing that comes out of that is it's possible I did the ANOVA, it said they're different. Now I run all my pairs and it says they're not different. Okay? And the reason it might say that is because the difference, right, the probability of type 1 errors for all of them to say there's a difference is 0.2 or whatever, for our example. Right? So we have to be a little bit careful. Very often, if ANOVA says there's a difference, then my recommendation is you go choose what's the one algorithm you want to compare against and do a pairwise t-test. ANOVA is not a paired algorithm, but it's very powerful because of what it does with the variances. Okay, so if I'm going to play with algorithms with the multiple t-tests, there's actually a way to put some of this together. There's what's called the BONFERRONI correction. So the easiest way to handle this is to look up the correction of the p-value and rough order. The BONFERRONI correction is if I'm going to do 3 pairwise tests, multiply your p-value by 3, and now say, is it confident at that? Because the p-value can actually do 2 things. We only talked before about the fact that it might actually have a type 1 error. Turns out the multiplication also causes increases in type 2 error. So if I go back to that same example, right, and I do the pairwise tests, if I do HC versus BMS, the p-value is 0.002. If I do HC versus SPMS, value is 0.014, and BMS versus SPM is 0.62. Okay, so now you remember what I said was the intuition. Let's go back and look at that for a second. Right? Oh, too many slides. For this one here, right, the healthy is 0.404 BMS, whatever, right? So we're now looking at what is the difference. So if I now go look at the pairwise tests, right, HC is different than BMS, statistically significant. Okay, the HC versus SPM, so this is the highest mean, right? And then the last pair was a little bit weaker. So if I take those and I look up the BONFERRONI thing, which is roughly multiplied by 3, my p-value of 0.002 becomes 0.006, still significant. The 0.01 becomes 0.04, which may or may not be significant. And the 0.62 wasn't significant to begin with. It doesn't really matter, so it's adjusted p-value. Okay. So for 3 groups, we have 3 comparisons. If we're only interested in asking the healthy group, how many corrections will we have to compare for? Well, in this case, and this is why I said you often want to go back and choose just the best algorithm. If I took my real hypothesis wasn't that they were all equal, right? That was what my null hypothesis was. My real hypothesis was my algorithm is better. So I can go back, and after I've shown that they're different, I can then do pairwise tests where I say, here's my algorithm against what seems to be the best of the others, and say, is it different? Okay, and then you get 2 comparisons and only 2 variables. Now, for everything I've talked about, all of this was us comparing things on 2 variables. So before I go on, any questions on this so far? I know it's a lot, it's coming at you fast. Okay, I would say the 2 most important things you should walk away with what we've covered so far are use t-tests or Wilcox tests or whatever for comparing your algorithms you against the state of the art. That's the ideal comparison. You choose one other algorithm, you do a t-test, paired if you can do it, because the paired t-test is most sensitive to there being a difference. If you're going to use a bunch of algorithms, you can use ANOVA, and it'll tell you there's a difference. And I forgot to add these slides, but I will talk about it separately. So here's a way in which I have seen, in my view, people intentionally cheat, and I've also seen people unintentionally get sucked in by this, using ANOVA or the related tests. So if I have 2 algorithms, right, and I'm trying to say, is my algorithm better than them? And I decide to actually include the top 4 algorithms. And by the way, this is better. Smaller is better. So here's I'll make my algorithm green. Right? So I have my algorithm. If I actually compared my algorithm with the next best algorithm, I might not be significant. But if I do my algorithm against the top 4, now ANOVA will say they're different. And that's fine, right? ANOVA is saying they're different. But if I actually use ANOVA maybe against the top 3, it might actually say they're not different. But I can always add another algorithm from the literature that's worse, eventually until it says they are different. And now, because experiments are sometimes, people say they're expensive to run, I'm going to take a smaller subset of data and I'm going to do a pairwise test between my algorithm and the leading algorithm. And sometimes that might be, again, if we have these algorithms that are overlapping, I might choose to only, not a valid curve, I might say that only this region is interesting to me. So now I change the metric, and instead of measuring performance over everything, I only measure performance in this range. Okay? Now, what I just did, I applied ANOVA over a large range, and now I'm going to do a t-test on a small range. Okay? The t-test on a small range is a different hypothesis. I switched hypothesis from something that was measuring maybe over the entire curve, and I said, yes, they're different, to only measuring them on a piece of a curve. So you have to be very careful. If I combine experiments to go from one test to another, that I'm comparing them in equivalent conditions, which is the cat and the octopus example I had in the beginning. If I choose a set of conditions, I might choose a set of conditions that let me draw a conclusion. That's not really the story being told. So you want to do all of your tests in the same region. So if I really want to do a test in this region, then ANOVA should be done in that region. But sometimes algorithms didn't all report all the data. So this is another common problem with computer science where you might have one algorithm, these algorithms doing this, and do I have a third color? So if these algorithms don't actually all exist in the same range, probably not a good thing that algorithm would always be better. If algorithms exist in different ranges here, when I go to compare ANOVA, I have to be very careful because I'm supposed to be taking performance over some range. So if I take the average over different regions, that's also not fair in how I use these statistics. So if one algorithm took an average over here, another algorithm took an average over here, and the third took an average over there, they're comparing different things. So their means can be different even though the algorithms have nothing. Because in fact, if I imagine taking this curve and I compare the mean from here to here and the mean from here to here, it's going to be different, right? So you have to be careful what you're computing statistics over. And you will sometimes find papers where they choose an error metric and you're looking at your head saying, why would they use that? Okay, and one reason they might use that is because that's the metric that let the statistics work for them. Okay, in a bunch of places, there's a metric that some people really love to use, and I believe it's meaningful in some ways, but not in others. And so if I have a curve, right, and so if I think of this as sort of performance at different parameters of my algorithm, right, so in face recognition, we often talk about false accept rates, right? So I could say, well, if I'm going to have a false accept rate of 1 in 1,000, or a false rate of 1 in 100, or whatever, right? I can have different values. I can ask about my performance at different slices. In fact, a slice this way is meaningful, and here I would have 3 algorithms. Okay, and here I would have 3 algorithms, but over here, if I took this slice, there'd only be 2 algorithms. This is how I lead into problems where I do one comparison with 3 and then another comparison with 2. Right? I have to be very careful when I cross this boundary because the blue line, I don't actually know what it's doing here. I can't say that here, I can say that for this test, I can be very clear in my hypothesis that at the value of whatever this value is, 10 to the minus 4, the red algorithm has higher accuracy than the green algorithm. But I can't actually say that it's the best algorithm because I don't know what the blue algorithm does there, right? To actually say it's the best algorithm, I have to be able to say blue does worse. And the way it's trending, does it look like blue's going to do worse? No, it didn't work there. Maybe I couldn't get to there in terms of my parameter. There's a bunch of things you have to be careful of. Related to this is this other measure that you will find in a bunch of computer science papers, and actually in other fields, called AUC, for area under the curve. And so since they don't and this is where they play a weird game. Since maybe not everything exists, or maybe they don't want to choose one operating point, they will do an area, and they'll compute the area under the curve, okay? And then they will compare algorithms on that. And the problem I've seen with that, maybe reject papers, is they're not clear for the area under the curve. What do I do for this blue one? Does the area under the curve for the blue one connect down here? Does it connect like this? Does it connect like that? Right? The blue one simply doesn't have data. Right? And as soon as it doesn't have data, area under the curve, in my view, is absolutely meaningless. Because it means nothing, because I don't know how to connect it. And I've seen people who report it, it's like, I don't know what this means. Any of these are possible. And they have a huge difference in what the algorithms are doing. So you have to be a little careful. If I can't, and the reason this often comes up is because people will say, well, they didn't report in their paper anything else. Right? That's why the blue line stops here. Because in their paper, they stopped computing here. And now I'm going in the state of the art, I'm going to push forward over here. Well, I can't really answer the question of what is blue doing. You can still do a comparison. You can have a meaningful statement, which is, of the algorithms that have run at this point, here's what I do. But if I try, and this is where people have done it, right? They try and say, well, the area under the curve for my algorithm, let's say that my algorithm actually did, well, it depends on if bigger is better, right? If bigger is, lower is better, right? The area under the curve, if I take blue straight down, right, and green keeps going like this, right? The area under the curve for blue might be better than green. But I don't actually know that blue goes straight down. If blue went over here, then maybe its area is larger. So there's a bunch of measures that go on. Statistics won't help you choose what's the right measures. But you might find that changing your measures changes the statistics. Okay? By far the most common, that again is very powerful in computer science, and you have to be careful, it can be used or abused, is a change of bases or a transformation. So if I have two things, if I draw sort of Gaussians, and I'm drawing them with means and standard deviations in regular space of x, right? Means, right? If I take the log of x, right? The mean of the log of x and the mean of the log of these two, they will both shift. They will do things. But standard deviation, remember the standard deviation formula is x minus x bar squared over n. If I change x by replacing x, let's do a simple transformation. If I replace x with 2x, what happens to its mean? Okay. So if x goes to 2x, x bar goes to 2x bar. The mean shifts. What happens to the standard deviation of x? Okay, so I'm going to take x minus x bar squared. So the answer, no, it changes. Okay. In fact, the answer to whether or not it gets bigger or smaller, well, so the answer depends on, is x bigger or less than 1? Right? Because if x was 1, if x bar is 1, then I have values around 1. So standard deviations transform. So when I change variables, if I go from feet to meters, oddly enough, my statistics test could change. Okay, but way more important than this is if I do a transformation like log. Okay, because this, x was linear. If I do this to my data, then what used to be a small variation, where here it can now become a huge variation. Right? It's increased a lot. So change of variables is a place where people will play games, but alternatively, it's a place where you might be looking for a different explanation of your experiment to make it significant. Maybe you shouldn't be using power, you should be using a log. Right? Change of variables might let you change how you interpret stuff. And it turns out there's a lot of psychophysical reasons and physical reasons why various things should be done in log space instead of in regular space. And vice versa, there's things that should be in regular space. So you need to understand what that is. Statistics don't change that. But sometimes you run an experiment and you don't find a difference. You might ask yourself, did I use the wrong variables? Okay, so a variation of this, which is a little bit different, is if I were to actually do certain statistics with where I actually look at X bar as the variable. So if I do a bunch of experiments where I use X bar versus the sum of X. Now the difference between those is, of course, 1 over n. Okay? But doing statistics on means versus sums is different because, again, of the scaling. Okay? It's especially important and difficult if in one problem I have n samples and another I have m. Right? Now you can ask yourself, and it's natural to say, oh look, I have a different number of data points. So I'm going to take the average because then the number of data points doesn't matter. And if you do that, you might decide, well, there's no difference between these. But the difference might have been how many samples there are. That might have actually been a big part of the difference. Right? If I'm asking clock tick questions and I'm doing clock frequencies, right, how many clock ticks I got for one or another, right, is actually maybe the more important part than what was the average. Right? So you have to be careful how you're looking at these things. None of those are statistics, but they're all important when you go to evaluate where your statistics are. So, and this was hopefully useful for you to do. I have more statistics stuff to talk about. We're going to talk about correlation and linear predictors and stuff. We'll do that next week. So the one thing I want to do before today ends is I'm going to set the schedule for who's talking which of the next 3 weeks. We have 3 weeks to go. I will talk a little bit more statistics, but Bob has to travel, so Bob is giving his talk next week. Does anyone else want to go next week for your oral presentation? Okay. Who wants to go the week after? After Rome? I got 2. We need 3. Okay. So we have 2 volunteers. I will choose the 3rd, and I will inform you who is in 2 weeks, and then the last 3 will be the week after. Okay. We are not going to have an exam in this class. Okay. But I've decided. So I'm worried that I'm presenting all the statistics. And I said we're not going to have an exam. I have a quiz. And the reason for that is I'm worried that people aren't really taking this seriously. A student who took this class the last time I taught it, where I did statistics, recently, and this is not true, so don't worry about it. I'm not telling you. Another student came to me, and it was clear they didn't remember anything except other than we had a statistics lecture. Okay? And while I am willing to help you with statistics, I want you to retain a little bit more of that. So I'm going to do an online quiz inside Blackboard, so there's no timing issues or whatever. And that will be done in the week of finals, so it'll count sort of towards your exam. I'm exactly not sure how much weight I'm going to put on it. I really don't want to grade it heavily, but I do want people to take the experimental design and the statistics a little bit to heart, so you might actually have to read through these notes. My guess is those of you who are here are doing that. The problem is not everybody's here. So I don't want them to get away with saying, you know what, I just blew off all those lectures, I'm going to write my own paper, and I don't really care what happened in class. So there will be a quiz on this. How much weight I give it, I'm not sure, but it's not a huge part of your grade, except that maybe if you haven't been here, maybe I'll weight it a little bit higher, I don't know. But post hoc statistics, like we've had a couple of people who've missed multiple classes. I'm not sure how to grade that. Maybe I'll just take attendance as part of the grade. But okay, so see you next week.